I'm very glad to stand here and share my work with you. And today my topic is about how to build a scalable read-write locks. And I believe that it is an ancient topic in this area. And I'm Liu from Fudan University. It is a collaborative work with Heng, Zhang, and Haibo, Chen from Shanghai Jiao University. First, let's take a look at this big picture, and it shows us how the synchronization primitives evolves from exclusive locks to read-write locks, and from read-write locks to RCU. We can see that we can treat semantic guarantees for a better performance. For example, by allowing multiple readers to enter critical sections simultaneously, read-write lock could achieve a better scalability compared to exclusive lock. And by allowing the readers to read the stale state from writers, and the RCU could remove the memory barrier and achieve orders of magnitude shorter reader overhead compared to read-write locks. So, but unfortunately, it seems to be that it is very hard to build a synchronization primitive that have both very strong semantic guarantee and very good performance scalability. And it seems that we need some new hardware support to get close the boundary to that yellow triangle area. So now we have HTM here, but I believe that it is not possible to remove the implemented memory barriers inside HTM. So in this paper, we focus on this point and try to optimize for some reader dominant workloads. And the goal is here. we will build a new synchronization primitive with same semantic guarantee with read-write lock, but has no memory barriers in the reader side critical sections. So before I talked about my algorithm, let's first see that some prior work. The first big reader lock from Linux kernel, and second scalable read-write locks, and use the scalable non-zero indicators like a tree to count the readers in a scalable way. And third is a NumAware read-write locks. It brings the ideas of cohort lock to read-write locks. It just simply if one lock if one thread unlocks on the same core, it tends to pass the lock to another thread on the same core. So that's why it is NumAware. But these three locks all contains atomic instructions or say memory barriers. So why it is the case? So Attia proved that in his famous paper that it is impossible to achieve a deadlock-free mutual exclusion without these two patterns, the read after write and atomic write after read. Basically speaking, to achieve a correct mutual exclusion, you should do two things. The first, you should announce that this thread will enter the critical section and allows others to see it, and then check if others is inside critical section. These two steps. Same thing happens to the atomic write after read. It's an atomic instruction. As it is an atomic instruction, you can first check if others is in critical section, and then acquire the lock in atomic operations. So we call these locks active locks. Active locks are in active locks, synchronization-related shared states are actively maintained and kept consistent all the time. For this case, it is read-write locks. The reader must first acquire the lock and make sure that all the others can see that I have already acquired the lock before it can execute the critical section. So it is not the ideal case. So we propose the passive locks. Passive locks means that synchronization related shared states for readers only becomes consistent when writer wants to check. And means in the common case, the execution of the query and critical section and release could be overlap or reordered, so to say. And as a result, writers cannot query reader states directly, but it can only wait and ask the readers to report. To be more clear, let's assume that this house is the rwlock, and I'm the writer and you are the readers, and we share that door. So if it is an active lock, I will stick a paper on that door, and when you get out the door, you make a mark on the door on the paper, and when you enter again, you erase that mark. So let's imagine that it will take a very long time for all the people to exit the door. But when it is a passive lock, if I'm the writer, I just stand here and shout, is anyone there in that room? So all I need to do is just collect everyone's report to me. And if I am not trying to acquire that lock, then everyone else could enter and exit the critical section, that door freely. So that is the idea. So let's look at a simplified version of the code. And when the writer tries to take a lock, it first sets its lock state to locked. And when a reader tries to take a lock, if it sees that the writer is intent to take the lock, it will report to writer that I'm out of the critical section. If the writer gathers the report from all the readers, it can make it is sure that all the reader is aware of its intention, and now it's safe for him to enter the critical section. But there is no architectural guarantee that if there is no memory barriers in the reader, so how long will the reader wait for it to see the newest states of the writer? But we have made some experiment that shows that the shared memory write becomes globally visible in a very short time, even without a memory barrier. So this experiment is conducted on the two large SMP machines with more tens of cores, and we just modify shared state on the core and try to read it in another core. If it's read still old data, delta time is collected, and this figure shows the cumulative percentage of the still readers. And so we can see that most memory writes are visible to others within around 400 cycles without that memory barrier. So, but there's still some problems. You can see that there is no memory barrier, so atomic instructions through readers, and we achieve correct mutually exclusive. So it seems to violate the order of law I just mentioned. But what is the case? The law of order states that it is impossible to achieve mutual exclusion, deadlock-free mutual exclusion with RAW or AWR. So, in fact, this algorithm is not deadlock-free. You can see that if the writer want to take a lock, and there is no readers try to acquire the lock, and so in this case, the writer cannot get any report from the reader. So the writer cannot decide whether a reader is inside or outside the critical section. So in this case, it will be deadlocked here forever. That is why we need to ask them for a report. If the writers find that a reader has not reported, it will send the API to these readers, and the handler is executed in the reader context, and it finds that it is not in the critical sections. It will report to the writer as it does when it acquires the locks. So there is a very very important property of IPA is that when IPA is when the API is received, the execution of the processor will be serialized. So if currently there is a overlapping execution of a query and a critical section, and here comes the API, the pipeline will be serialized, and there won't be any reorders across the APIs. And in that way, that readers it allows writers to always read the correct state of the reader. So, so someone may complain that API is very expensive in our machine, so it is not. You should not use API on synchronizing primitives. But according to ours and others' experiments, the API is actually cheap in modern hardwares, and the latency is around 1,000 or to 2,000 cycles in average between send and then the API is received. So this overhead is similar to less than the cross-socket cache contention. So, but then now the story has not ended. A correct lock semantic must guarantee must have a strong visibility guarantees. That means that readers and writers must see the newest states of each other upon entering the critical section. For example, in this case, writer just exits critical section and reader enters the critical section. If the reader could read the stale data that the writer had modified, but in this critical section, and it will violate the read-write semantic. So our algorithm relies on the TSO consistent model to keep this guarantee. And TSO consistent model is well adapted on many processors, such like x86, Spark TSO, or IBM Z series. So when in the previous example, when the reader says that the writer is unlocked, so they sees the free that the writer has just write. According to the TSO consistent model, it will be guaranteed that the reader could see all the writer's modification to memory before that assignment to K. So let's make it whole and have an example. There is four readers, and the writer is not shown here. The first, the writer will set the writer status to locked, and the reader 1 exit its critical section and reports that I'm out of critical section, and reader 2 tries to enter the critical section, but he finds that the lock is locked in writer mode, so he just reports I'm out of the critical section. The writer found that the third writer and the fourth writer is not reported, so they send API to both of them. And the third writer, the third reader is not in the critical section, so the API handler replies that I'm out of critical section. And the fourth reader finally finished its critical section and reports I'm out of the critical section. It is now safe for the writer to enter its writer critical section. There's some insight that IPS actually introduced a new dimension in designing concurrent algorithms, and API can be used to inspect status on remote cores without caring about instruction ordering or memory consistency in this case. So memory barriers in hard paths can be eliminated in this way using API. So as I showed in the previous example. So there's more topics in the paper. As time is limited, I will cover them. So we developed a new sleep and wake up mechanism for kernel, and allows multiple sleeping wait readers to be wake up in parallel when the writer's releasing lock. We also developed developments of support for sleeping inside reader critical section, and a user level algorithms and also a user-level RCU algorithm based on this. So let's see some performance results. And the performance evaluation is conducted on the 64 cores AMD Opteron machine with 256 gigabytes of memory, and the software is Linux. And we just made around 20 lines of manual modification to kernel to incorporate our algorithm into it. So what we compare to is the effort to using RCU to parallelize the virtual memory management, and it appears in ASPEROS 12. So it's using using RCU to protect the address space of a thread of a process. So the workload is histogram, medicine, P-search. The first one is MapReduce program with many file page fault, and second one is it's also MapReduce workload with many anonymous page faults, and third one contains a lot of mmap and unmap. In this case, the mmap and unmap takes the rwlock, and the page fault takes the rwlock. So let's see the performance. For the histogram workload, you can see that our passive rwlocks performs much better than other systems. So it means it's because that in the RCU VM, so the only optimized for the anonymous page fault, but not the fail page fault. So in this case, we could perform much better. And for the Metis, as it is anonymous page fault dominant, so our systems perform similar to the RCU VM. And third one, and in this case, as its system performance is bounded by the mmap and the unmap, in the RCU VM, the mmap could be parallel with the page fault execution, so it achieves better scalability compared to us. But the RCVM implementation modifies around, I remember that is more than 2,000 lines of kernel code, but we only need 20 lines of kernel modification. So I think it's worth it to have such a performance difference. And here is a Microbenchmark. We have 63 reader thread and do the lock and unlock operations repeatedly, and one writer locks the rwlock, unlock it, and wait for a time. So we alter the delay latency and see measure the reader's performance, reader's throughput. You can see that the passive rwlocks achieve a much better reader and writer performance compared to big rwlock or traditional rwlocks. It means that it is mainly because that we remove the memory barriers in the reader correct sections that lead to such a performance difference compared to big rwlock. So there is some performance numbers of the row latency of the primitives, and you can see that the rwlock only needs around 12 cycles to acquire or release a reader lock. And for the writer, if there is no readers, the rwlock should send 64 IPIs to all the readers. So in this case, the performance is the worst, around 60,000 cycles. And if it is 63 readers, and its performance is much better than the other three alternatives. So we believe that it is a common case for the use case in for a read-write locks. In a common scenario that we're using read-write lock, the writer should be much more than the number of readers. The readers should be much more than writers. So let's draw a conclusion here. We designed a new read-write synchronization mechanism called passive read-write locks, and it maintains the same semantic guarantee with rwlock, but have the competitive performance scalability to RCU, and by eliminating the reader side memory barrier. And it opens a new way of implementing memory barrier-free algorithms. You can utilizing short memory staleness latency or cheap IPI, or you can using IPI to inspect remote states. And third, you can try to take advantage of TSO consistent model to design some new concurrent algorithms. So there's I heard someone that designed a barrier-free work stealing algorithm based on the TSO, there's a TSO machines. Yeah. So thanks. I'm ready to take questions.